My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Today it's our 110 International Physics webinar. So good afternoon to all here in Bangladesh and a very good morning to all those who are watching this program live from UK. So hope you are well and safe from corona pandemic. So all we know that we are staying in a corona pandemic situation, so we cannot continue our normal academic program inside the campus. So we have to start our online program. So I think you have already come to know that our Department of Physics, Pabna, University of Science and Technology has started its online program, including online international physics webinar. And we have successfully completed our 109th international physics webinar, and today it's our 110. We are trying to adjust with this new normal situation. So today I would like to welcome you all to a joint session between the Department of Physics and the University of Salento and INFN division. And we have with us here today Dr. Professor Andrea Ventura, Associate Professor of the Mathematics and Physics Department, University of Salento, and he has already connected with us. So, well, sir, welcome to our International Physics webinar. So, good morning in your part and good afternoon here, sir. So
yes,
thanks for accepting our invitation, sir.
Okay, many thanks for this invitation in this international webinar. I am very proud to be with you in Pabna, for just virtually, but this is a good chance to share our experience.
It's also my pleasure, sir.
Many thanks. So my university is in Italy, and my research is on behalf of the National Institute of Nuclear Physics, INFN, for the division of Lecce. I will talk you about searches of new physics with the ATLAS experiment at the Large Hadron Collider at CERN in Geneva. So we will take a journey toward the infinitely small. You know that infinitely is not a physically defined word, because it's just a mathematic way to say something very, very large or very, very small in this case. So in this picture, we can have a rough idea of what we can see, different sized objects, and what do we use to see these objects. So we can start from the middle. With our eyes, we can take a look at a dog, at mountains, or small objects. But if we want to see planets, satellites, stars, and galaxies, we need observatories, we need telescopes, and so on. And we can explore up to 10 to the 25 meters or more. But if we go in the opposite direction and we want to study cells, DNA, for instance, we need microscopes or electron microscopes. But to move at the level of atoms, nuclei, or smaller particles, necessarily we need accelerators. And the higher the energy of the accelerator, the smaller dimension we can explore. So in the end, elementary particle physics allows us to study the universe moving from the less than 10 to the minus 18, or even 10 to the minus 12 is the frontier, up to intergalactic scales. And in a certain sense, these two borders, these two edges of this scale, in some way connect each other, thanks to cosmology and other studies. What I will focus on is, in this talk, are elementary particles. We can start from a water droplet, which the typical dimension is 1 millimeter, and then go in smaller and smaller dimension. So a water molecule is of the order of a nanometer, 10 to the minus 9 meters. This is made up of 2 hydrogen atoms and an oxygen atom. And In particular, the hydrogen is made up of a proton and an electron, which are connected thanks to the photon, which is the mediator of the electromagnetic force. The proton is not really an elementary particle. Its dimension is of the order of 10 to the minus 15 meters, a femtometer, but it's made up of 3 quarks up and down, whose dimensions are less than 10 to the minus 18 meters. We can say that these are like points, no dimensions. And they are put together thanks to gluons, which are the mediators of the strong force. And we don't know what the quarks are eventually made about. Elementary particles can be divided into big categories. You see in yellow and in red, the leptons and the quarks. And in particular, the up and down quarks and electrons and electron neutrinos, which are the first generation of matter, is what is called the ordinary matter. The other 2 families, which are made up of charm and strange quarks, and muons and neutrino muons for the second generation, and then top and bottom quarks, and tau and neutrino tau for the third generation, are kind of a higher energy matter that is not usually available at the level of the ordinary world, but can be created in a laboratory by smashing particles one against the other and produce higher energy states so that we can produce higher mass particles. So the yellow and red part of this graph essentially is matter, while on the other part we have the known forces. The green blocks shown here are the known forces, which are the electromagnetic force mediated by the photon, the nuclear strong force for the gluons, and the Z and the W bosons, which mediate the neutral and the charged nuclear weak force. There is also the gravitational force, which is not easily put together in this model, which is called the Standard Model. In 1967, Steven Weinberg and Abdus Salam formulated a unified theory in which the electromagnetic and the weak interactions were put together, and the same was also theorized independently by Sheldon Glashow. So this was the birth of the Standard Model. In particular, the electromagnetic force with the photon and the weak force with the 2 charged W and the neutral Z boson, they are mixed together. Starting from a no mass eigenstate, they get some mass, the W and the Z in particular, while the photon remains massless. So we get into new mass eigenstates with the non-zero mass bosons, thanks to a mechanism which is called the Higgs mechanism. That is been theorized not only by Peter Higgs, which is shown here in the lower part of these photographs, and also by Broad and Engler in BEH mechanism, also called, for the spontaneous symmetry breaking. This mechanism has been searched for almost 50 years, looking for a Higgs boson, and this search only came to a final result in 2012. So from the middle 60s, it took almost 50 years. And in this presentation, we will show some main steps that brought from this simple theory up to the experimental discovery. So what is the Higgs mechanism? It's very hard to explain for non-physicists. Fortunately, here we have the audience is surely prepared to some fundamental notions, but this picture was thought for an outreach purpose for a general public. So the painter here, David Miller, a British painter, produced this sort of comic in 3 steps. So to explain the Higgs mechanism, you can think at a party in which a lot of people is there. They actually don't know each other much. They are just chatting slowly and quietly, having their drink, waiting for something to happen. They don't even know what is going to happen. So it is a quite starting situation. At some point from this door on the left, a very important person appears. You can imagine a famous scientist. It can be Albert Einstein, for instance. And immediately somebody realized about the presence of this very important person. So they start thinking that they want to interact with him and try probably just to chat quickly, just to touch him, just to ask him something very quick. But at the same time, what he probably wants is to go on the other side of the room to take some cocktail or some sandwich just to have the party like everybody else. But unfortunately, this is not easily possible because everybody wants to jump to him and try to stop him to have a chat and try to interact. This is what happens when massless particles goes through the Higgs field. It acquires mass because while before getting in this room, Einstein could easily move because there were no people to interact with. In this part of his path, it becomes very hard to move. So he acquires mass. There is some inertial translational resistance. So in the end, he gets some mass. So in this way, it can be explained how a mechanism determines some mass, some translational inertial to movement. In general, the Higgs boson is very important also for cosmological reasons, because this particle, which is studied at CERN, plays an important role in the theory of the Big Bang when everything started. So at time 0, let's say, until the 10 to the minus 34 seconds, the Higgs boson brought to the so-called inflection, and it brought to the production of the very first particles. And until 380,000 years, the cosmic radiation following after this Big Bang could not be observed because light could not move through, and the world was just dark, so we cannot have evidence before this time. Later, after that the light could propagate and other particles can be produced, we can move after 13.7 billion years to the present world. So the Higgs boson can explain the homogeneity of the universe as we know it today, with a 2.7 Kelvin temperature and all the ordinary particles that we know. So moving from the left to the right means moving from the origin of the universe until today, so moving toward the future. But this also means moving from higher energy to the lower energy, the smaller, lower temperature that we have today. In some sense, if we want to recreate the conditions of the original universe, we need to move from right to the left. So increase the temperature means to increase the energy, and so to get higher momentum beams with particles smashing at more and more powerful accelerators. And this is what we need to do. For this reason, science has come to have the largest laboratory for nuclear research in the 1950s with the CERN, European Organization for Nuclear Research, also known as European Organization or European Laboratory for Particle Physics. It is one of the world's most prestigious research centers, also beyond the particle physics and physics in general. And there are 80 countries all over the world participating to this World Center at CERN. Here are some pictures. Since more than 60 years, CERN hosts the largest experiment for high-energy physics searches. And here you have also a sketch of the accelerator system. This is made up of larger and larger circles, meaning moving from the protosynchrotron to the super protosynchrotron up to the LHC, that is the Large Hadron Collider, which is the largest particle accelerator in the world. But in the beginning, this big circumference, which is almost 70 kilometers long, 100 meters below the ground, from France to Switzerland, was called the Large Electron Positron Tunnel, the LEP. And for about 20 years, it has hosted electron to positron collisions, and with the possibility to perform very precise measurements of the standard model in the electroweak sector in particular. Also searching for the Higgs, but unfortunately no chance to find it until 2001. And the best performance was to put a limit, just to say that the Higgs mass was not lower than 114 GeV. But that was not much. It was just a limit, not a discovery. So the purpose was to move to a higher energy collider, smashing protons to protons, so hadrons. This is the reason why we call it the Large Hadron Collider. From the pictorial point of view, the LHC runs about 100 meters below the ground in the Geneva area. And there are 4 big experiments in 4 main points around this circumference. We have Atlas, ALICE, CMS, and LHCb. These are 4 very large experiments. In particular, Atlas and CMS are the 2 general purpose experiments. And in particular, I will talk you about Atlas, which is the experiment I belong to. It is in the Marine site close to the border between Switzerland and France, in the point 1, it's also called. This is an aerial view of point 1, and here is the underground cavern, the shafts that you need to move through to get to the underground point 1 area. Oh, this picture gives you an idea of this tunnel, 27 kilometers long. You can go there with electric motorbikes, bicycle. You can go jogging if you prefer. There are almost 2,000 dipoles. You see these blue cylinders. In these dipoles, the beams are made run at a velocity close to the light velocity, 300,000 kilometers per second, at a temperature that is lower than 2 Kelvin. So it is colder than the universe. This is a sketch of the ATLAS experiment as it was designed in the 1990s. On the left, you can see with the correct scale. And to have an idea, just consider that 1, 2, 3 persons are designed here below on the ground. And this gives you an idea of 24 meters height and about 44 meters length for 7,000 tons weight. And the different colors represent different technologies to reveal particles, different kind of detectors. Moving from the innermost part where the protons smash, you can take a look here on the right to see how this works. So there are a large quantity of tracks produced that go through an inner detector in light green, where the charged particles are observed. Then you move through the calorimeters. You can see in the electromagnetic calorimeters the photons, the electrons in particular. And then you have the hadron calorimeter in orange, which allows you to detect the neutrons, the pions, the kaons, the protons. And then in the largest part, the outermost part, which is designed in cyan, you have the muon chambers, both in the barrel, cylindrical central part, and in the 2 end caps on both sides. The muons are more penetrating particles. And there are also neutrinos which actually escape the detection. And you can only reconstruct them through the difference in energy balance. This picture is after the lab program. The cavern at point 1 were prepared to the arrival of ATLAS. And here you can see the feet upon which the entire detector is installed. So these are just the feet, and you can see how huge they are with respect to these 2 technicians here. Later, the toroids, which characterize the shape of the ATLAS detector, in particular its magnetic field, they were slowly brought down in the cavern. All of them, these are 28 meters long. They can produce a magnetic field up to 2 Tesla. So this is really a big technological challenge. And here in this picture, which is in 2005, the entire structure of the 8 toroids has been prepared. And here you see how small is this person here in the center below of the picture. This is a famous picture. If you find it on the web very easily, the Ravensburger prepared a puzzle for children, and not only for children, also for very hard to realize. Later, the inner detector was put in the central part of the ATLAS experiment. This allows very precise measurements at the level of 10 microns. And this is very important for so large volumes. So everything should have been ready for year 2008. Everybody was excited on the 10th of September because the LHC was starting with circulating proton beams. First in one direction, then in the opposite direction. And the step later was to make these two beams smash one against the other. But unfortunately, things didn't go in the best way. And after just 9 days, on September 19th, there was a severe accident due to a big helium loss. Unfortunately, this was a very severe damage. The temperature that slowly was put down to the project 1.9 Kelvin immediately increased because of this helium loss, and many months were needed to recover the machine and to make the beam circulating again at a lower momentum with a warmer time scale. So it took March of 2010 to have again beams and the first collision at 2 TV, which was the record, because until that moment the world record belonged to the Fermilab experiment, Fermilab accelerator, and the CDF and D0 experiments. So it was time for the ATLAS people to train to make the experiment work in the best possible performance, and also to normal people, students, to come and visit the ATLAS experiment, at least the control room in the surface at point 1. And after 1 year of data taking, December 2011, there was a public ATLAS CMS seminar announcement. This is the agenda. It looks quite anonymous, but it has been the first important step toward the discovery of the Higgs boson. As you can read in the agenda, there were updates on the standard model Higgs searches in both ATLAS first and CMS later, and then a joint question session. But actually, this was the start of a very important discovery. What was shown was a first possible evidence of the Higgs boson. So in this plot, you can see the 95% confidence limit on the strength mu for the discovery of a mass as a function of the Higgs mass. So you see the black continuous line superimposed to a dashed line, which represents the standard model scenario without the Higgs. And in the green and the yellow band, you have the width within which you can claim for agreement within 1 sigma or 2 sigma, respectively. So to have an evidence, you need to be at least 3 sigma far from the expected, and means to be outside, significantly outside the yellow band. And this was happening at that time, essentially around 130 GeV here on the left, and probably also around 400 GeV here below on the right. But to claim for the observance, you need to be higher than strength 1, that is the blue dashed horizontal line. This announcement was made on just less than 5 inverse femtobarn, which means the statistics that was collected until that moment in December 2011. And during the 2012 data taking, the collected statistic increased in order to improve the statistical significance and see if definitely this apparent peak was just a statistical fluctuation or it was indeed a new exciting discovery. So data collected during 2011 plus 2012 were collected. The black dots here represent the experimental data. The blue continuous line represents the background only. And when you try to fit the data with respect to the background only, you see that there is a strong disagreement around 126 GeV, which is better explained if you consider a new source of physics that can be a new boson. You can see below the data minus fit residuals, and you see that around 126 there is a small peak. This was in the search for Higgs boson decaying into photon-photon. The announcement of this channel was not the only one. Also, another interesting channel represented by Higgs going to Z couple, and finally 4 lepton channel. You see that the agreement between the Monte Carlo with the background only, that is in red, and the data is okay, except for this area around 125 GeV, which can be explained with a new signal for Higgs mass around that region. So these are the data as they were shown in July the 4th of 2012 as the start of an important international conference, which were held in Melbourne. It was afternoon in Melbourne. It was morning at CERN. Most of us were there. And here you can see Fabiola Gianotti, who at that time was the spokesperson of the Atlas experiment, together with Joe Candela, the spokesperson for CMS, showing these results. And we can say the gotha of the high energy scientists all over the world. You can recognize somebody here in the main auditorium at CERN, observing this new particle. But still not sure it was actually the Higgs boson. It was just a new boson. This was announced like this because we wanted to make sure that this was actually the Higgs boson. So it took almost 1 year to have this information. And at the same time, the Higgs boson became quite popular. This is an example of how the Higgs boson was made interesting also for non-physicists. So some people in Italy has invented the sonification of the Higgs boson. So just imagine to put the experimental data on top of a musical score, just like the Atlas data were musical notes. So you can get a symphony, which is quite quite random, I must say. But at some point, you see this very, very high data, high frequency notes, let's say, and in some sense, it sounds like the Higgs boson appears in this way. Okay, this is just fantasy, it's not real science. We were just waiting to understand if this boson is or not the Higgs, and it was, because the spin of this particle was proved to be 0. So this is a scalar boson, not a vector boson like the other ones. And this was considered like the definite proof that this is the Higgs boson. In the summer of 2013, the EPS HAPP prize went to the Atlas and CMS collaboration in persons of the Della Negra, Ienni, and Wirde, which were the spokesperson during more than 20 years. And this was just the prelude to the Nobel Prize, which went in December 2013 to Peter Higgs and Francois Anglard. And in Stockholm, this was a big announcement, and also the Atlas and CMS experiments were cited because the discovery was only possible thanks to the work of more than 5,000 scientists from all over the world. Later, more and more precise measurements were performed. This is the measurement of the Higgs boson mass, which joins together Atlas and CMS data. And you can see in this black area that it is around 125 GeV. So the Atlas collaboration covers more than 180 institutes of 40 nations with 3,000 physicists. What you see here are in yellow are the nations of the institutions. But actually, if you consider the nationality of each single person, you can get to more than 60 nations, because there can be people from, don't know, India, or probably also Bangladesh, I don't know, that moved to some other institution all over the world and then could take part to the Atlas collaboration. But this is becoming larger and larger experiments and needs a lot of manpower. So I really hope that you can enjoy these big experiments. This is a very small fraction of the experiments. We are just a few hundred people here in Atlas Week, which was held in Copenhagen. And it was a very sympathetic situation, because we were on a floor in which the Atlas script was prepared. So we took this picture. We want to make particle physics also interesting for high school students. We have the international MasterClasses of particle physics. Students come to our laboratory and live their experience for a day as a researcher, participating to they perform some simple experimental measurement, and in the afternoon they come to a video conference connected with CERN and other institutes, and there are gadget prizes at the end of the day. We organize student visits at CERN. Unfortunately, we couldn't this year because of the pandemic, but at least we had the chance to meet in this international webinar. This is a very interesting chance for all of us. And we are moving toward new discoveries. So after the run 1 and the run 2, which has been taking data from 2015 to 2018, we are moving after this long shutdown toward the run 3. And the energy will move from 13 TeV up to 14 TeV. But the next frontier is toward the high luminosity phase, which should start from 2026. Probably we will take 1 more year because of this delay due to the COVID-19 pandemic, which is slowing down operations. But from the software point of view, we are moving very, very fast. So what do we want to discover? What is beyond the standard model? Well, we have proved the existence of the Higgs boson, and we want to verify if there are other theoretical models that can answer the unsolved questions, including the supersymmetry, which is one of the most elegant theories and which could explain the dark matter, can explain the broken symmetries in nature. We can discover new massive vector bosons, like the W and the Z, but at higher energies. We can probably find exotic long-lived particles or micro black holes or extra dimensions. Like we think we live in a 3+1 dimension world, but maybe there are other dimensions which are simply squeezed or hidden somewhere, and moving to higher energies, we can discover that. So supersymmetry is for sure one of the most searched since 50 years. And it predicts that the standard model particles, here on the left, have a supersymmetric particle, which is represented here on the right. And each one of them has a larger mass with respect to the standard particle. It's like we are on top of a lake, and we see boats or ships on top of the surface, but maybe below there are hidden below the surface larger particles with the higher masses. And these partners are bosonic when the standard particle is fermionic and vice versa. So it depends if the spin is integer or half integer. Supersymmetry researches cannot be explained just in a few words, since we are not still being able to discover supersymmetric particles like sparticles. So there should be quarks, leptons, Or instead of neutrino, you can have neutralino. Instead of W bosons, you can have charginos. Well, you can only try to move to larger energies and try to cover an entire mass plane, trying to find some evidence for disagreement with respect to the standard model. But until now, after 10 years that the Atlas data taking has started, we have put more and more stringent limits, but still we didn't discover supersymmetry. So you can see how this area with the same scale is becoming larger and larger. We are excluding more and more large areas, but still we are not discovering the SUSY, and we hope we will be able with the future runs at the LHC. Let's hope to find something, because this will be the new frontier of high energy physics. So I come to the end of my webinar. I want to finish. Thank you all with this picture of the universe. The painter is a French one, is called Camille Flammarion, and you can see a very courageous person trying to move beyond the known of the old world, the ordinary world as we know it, with the sun, the moon, the trees, and he discovers something completely new beyond, with different shapes, colors, something imaginific, of course. It's not real, but this gives you an idea that if we want to improve our knowledge, we have to think different. We have to go beyond the normal appearance, and only science can really do it. And is what we do with the particle physics at CERN in Geneva, and 180 different institutions, including University of Salento, Lecce, INFN in Italy. Thanks for your attention.
Thank you, sir, for your wonderful presentation, sir. So if you allow, we can start our discussion session. So we have got question in comments. So, sir, why the wave function collapse when we see an electron?
Well, the presence of a new particle when present in the field at so high energies can only be described with quantum mechanics laws. So you cannot describe it from the classical point of view. You need to have a theory beyond. What we do from the experimental point of view is to reconstruct the tracks that come from the collision, okay? So we can just say if a particle is being produced, what can be its momentum, its energy, the trajectory, and then try to get information also on its spin, on its mass, then to identify. So what we need to do is to give all the instruments to the theorists to get a final answer to the unsolved questions.
So thank you, sir. There is another question in the inbox. So is it possible to create dark matter and dark energy in LHC or Atlas?
Well, this brings me to the black holes in particular. This is a possibility. The dark matter needs, in particular cold dark matter, needs a candidate. And you need to think at it as a neutral particle, so electrically no charge. And it needs to have a large mass. indeed, because we need to explain for 96% of the unknown. We just know the 4% of the ordinary matter, and not only dark matter, but also dark energy. Well, I think that we can, at the LHC, we can give some answer on dark matter. In particular, the supersymmetry, the R-parity conserving supersymmetric theories can have a candidate. For instance, the neutralino can be a candidate for the dark matter. You have to imagine that the LHC, if you are able to produce gluinos or squarks, then they will have to decay along chains, producing both supersymmetric and standard model particles. But in the end of the chain, you will always need to have one supersymmetric particle, and if our parity is conserved, and the lowest mass supersymmetric particle cannot decay into nothing else, so it has to survive as it is. It is not detectable, since this does not interact electrically. You cannot see it with other means, and this is a good candidate for the dark matter. Until 20 years ago, we thought that maybe the neutrino could be an explanation, but this is for a very small fraction. And we hope that the neutrino can contribute in explaining this dark matter. But maybe this is not the only answer, and we need to explore data also from the astrophysics point of view, not just from the collider physics.
Thank you, sir. We have another question. Could you please explain once more the supersymmetry?
Well, supersymmetry has been theorized for the first time more than 50 years ago, because the decades are passing through. You have to imagine a parallel world like we have now. It's something conceptually similar to have a positive and negative charge. So you have matter and antimatter. So you have to imagine matter and a supersymmetric matter. And of course, also the antimatter has a supersymmetric antimatter. It's a kind of super world, but you never found it so far, simply because the mass of these supersymmetric particles, which are also called sparticles, is too high to be observed at a normal accelerator. Maybe it is hidden at a very high energy, and you can only reach it by smashing particles at huge energies that we didn't get so far. We are at 14 TeV energy, but we are moving to higher energies in the future decades. So think at the FCC project, the Future Circular Collider, which will be 100 kilometers circumference. This is the goal. So there is a lot of work in front of us. Probably we are talking about the 2050s. So we need many, many years to move there. But we have to get ready now if we want to have new physics then. And the supersymmetry can be the possibility. Clearly, you have to imagine that these particles, whenever produced, vanish immediately. It takes less than 10 to the minus 25 seconds, and then they convert into some standard model particles. So it's very exotic, and let's hope that we will be able to find it finally.
Thank you, sir. So there will be the last question. So some students actually want to know how they be a part of CERN or ATLAS. What they need to do for that?
There are many ways. Just go to CERN.ch site. There are programs. First, for to taking a virtual tour. That is the easiest thing to do. And then try to go there as a high school student or a summer student. There are many programs. Unfortunately, 2020 was a very unfortunate year. But you can go there for internships from 3 months to 1 year and take your degree, try to find some researcher or professor working there. I mean, just go on the web and find all the results. A very important thing to remember is that the web, as it is now, the World Wide Web, www, was invented at CERN in the early 1990s, and with no profit. Not one single dollar was gained directly with this invention. It's incredible how the fundamental knowledge can be used for the benefit of the entire humanity. This is very important. So if you want to become a physicist, go this way and try to study new particles. Maybe at some point you will discover something different. You will become probably an engineer. You never know. But start from the curiosity, wanting to know more, to understand how the world works, the universe. Okay.
Thank you, sir. So I think students have learned a lot of things about particle physics and CERN and Atlas. So thanks for accepting our invitation, sir. So we'd like to say thanks on the behalf of the Department of Physics.
I was honored. Yes, very thankful for this invitation from your side.
Yeah, thank you, sir. It's my pleasure, sir. So
have a nice day.
Bye for today, and hopefully in near future we'll arrange another webinar with you, sir. Bye for today. And after the COVID, I'll definitely invite you to visit my university.
Yes, let's hope to have this chance. It would be very, very interesting. Have a nice day. Bye, everybody.
Yeah, bye, sir.